Okay, so before starting today's lecture, I have to maybe notice quiz 2. Okay, next Wednesday we will have quiz 2. Okay, so it is open book quiz as before, right? So, but no electronic devices are allowed. Okay, only paper materials are allowed, and the coverage is all course materials. But yeah, compared to previous quiz, I think it would be easier because we will only raise the multi-choice questions. Okay, you can select one, maybe one or two, three choices. Yeah, so you can just select, not write down. Okay. I will raise 10 questions. Okay, so that is the quiz 2. Okay. And so last time we learned about the visual language model, right? So briefly review these GPTs and BERT and the clip, right? This clip is nowadays very popular. So there are text and image encoder. You will train that text and image encoders using this contrastive learning. Okay. And in the testing, by inputting some unseen classes as some word, some prompt, you can perform the zero-shot classification. Okay. So this kind of the model trained by the large-scale data is nowadays called as foundation model, right? And nowadays the trend is making this kind of the model trained by the large-scale data and testing on some zero-shot, testing on in the wild data set in the zero-shot manner. That kind of trend is popular these days, I think. Okay. And also, when aligning with image features with the text feature, this kind of zero-shot capability, the generalization capability is increased, actually. Okay. So this is the method for training the clip. And we use a lot of image and text pairs from the web and use it for training the clip encoder, text encoder, and image encoder. Okay. And it exhibits the excellent zero-shot classification performance. Okay. And also it is generalized to different styles as well. Okay. Okay. And also we learned about some techniques that makes this clip generalized to some regions of the images. So clip encodes the whole image and the text pairs, but this region clip, they can align these sub-regions of the image with the text prompt. Okay, that's the region clip. And also similarly, glib is proposed, and at the same time, in the same this region clip and glib, they are both published in CVPR 22. Actually, they are concurrent work to make a clip extended towards the object detection task, localizing the object. Okay, that is the glib or region clip. Okay, and also combining this kind of text signals to the state-of-the-art transformer-based object detection pipeline, which is the DINO. DINO was the transformer-based state-of-the-art object detection pipeline. Okay, it's an extension of DETR, right? We combine this DINO with some language models and make this achieve the object detection with some language prompt. Okay, so in here we say this is the image this is the image input and this is the text prompt. And we somehow combine these two features using the cross attention mechanism. Here, it is detailed here, right? This is the text prompt and this is the image input. And we combine them to generate new combined features, okay? And also, here, this is the language guided query selection. So before inputting the input image features, we have once more select the queries for image features. And also for the decoder of the transformer, the Dino, we combine the language signals again. And at the end of this header, that predicts the object bounding box and image class. We also combine it. We somehow train it like the clip, okay, using the contrastive rules, okay. So that's the grounding demo, okay. It also exhibits the generalization capability, okay. So currently, this grounding deno is better than previously introduced clip or other region clip things. Okay, yeah, this is the state of the art and have more, have better characteristics compared to previous. Okay, so this is the normal way to combine this text signal and the image signals. So this is the image feature extractor, and this is the text feature extractor, right? And this is the actually object detection pipeline that first extract image feature, and this is neck, and this is head. So here we estimate the classes and also the bounding box, okay? That is happening in the last part of the object detector. So this is the feature extractor, and this is the intermediate layers, and this is the last layer to estimate the classes and boxes. But we concatenate the text features in the middle of the object detection pipeline, okay? That's how we combine, in most of language-based object detection pipeline, they are approaching this. Okay, in the middle of the object detector, they combine the text features. Okay, that's the thing. But here, here they say fusion paces. Fusion paces. That was happened in A. So I'm not sure you are, maybe you can able to see this. This is A, fusion B, and fusion C, okay? Fusions are happened normally in some partial ways in previous work, like clip and region clip. Mostly they combine language features in the early phase or at the last phase only, okay? But in grounding deno, they try the early, late, and also intermediate. So that is indicating the A, B, and C, okay? And also text prompt, that was represented in either sentence or word, okay? So sentence is composed of multiple words, okay? That's sentence is two, how to say, two cores, and word, it can be two dense to represent the text prompt. So in grounding deno, they try to use the sub-sentence, okay? So this is sentence level and this is the word level. So this encoding can be too dense when we use the word. And when we use the sentence, it could be too simple, right? So here, they are basically based on the word, okay, to capture the dense representation, but they are, how to say, prone some of the connections here. So to make the sub-sentence level text embedding. So this is also proposed in grounding deno. So two characteristics, they combine text and image features in all levels of the hierarchy, and also they prone the some representation for the text embedding. So that's another good thing happened in the grounding demo. Okay. And I want to also explain this segment anything. Okay. Maybe this is the method proposed in some recent technical report. Actually, these slides are newly added to the previous lecture slide. Okay. Actually, the lecture slide is updated. So this is some technical report by Meta AI. Okay. And this is also some famous foundation model for segmentation. So previously we saw some works for object detection and classification, right? But here I added some segmentation foundation model. So what their aim is similar to previous. So they want to learn some model, some transformer-based model using large-scale data. And their aim is generalize in unseen domain data. Okay. This is actually the zero-shot segmentation, right? This is what they want. Okay. And also, their input and output looks like this. Okay, so this is their output, and this is input. This is output, and this is input, and this is the model they want to train. Okay, and this is some prompt. Okay, so this is they can have one of prompt here, so they can only have some point indicating 1 point for. So if they this is the image, right? Having humans and some background here. And if you get 1 point for this, then the output you want might be the segmentation mask for this human, okay? So they want to do that kind of things by inputting this prompt, this point prompt, okay? So when you input the point prompt, your output, you expect that your output can be some segmentation mask that include that point prompt, okay? So, and also the other prompt could be the bounding box, okay? So in the image, if it looks like this, and if you input some prompt, the bounding box prompt like this, then your segmentation output, maybe you may expect is like this, okay? And this is some segmentation, some rough segmentation mask, then the output should refine this, okay? That's another prompt. And another prompt could be some text, okay? This is also some text. So there could be multiple prompt, okay? So given prompt and also image features, you want to estimate new valid mask, okay? So yeah, the task is promptable segmentation, and model is doing this using the transformer-based model. And data, there are 1 billion masks, okay? So using this large-scale data, you can train this researchers in Meta AI, they train this segment anything. Okay. So again, the pipeline looks like this. This is the image, and they first encode the image, and using the prompt encoder, they input it to decoder the prompt, their features, and also the image feature. Okay, and via the mask decoder, which is the transformer decoder, you will get some candidate masks. Okay, and they adjust the candidate, always predict 3 candidate masks. It was heuristically designed. Okay, so they always output 3 candidate masks. And image encoder, that's the vision transformer. Prompt encoder, points and boxes, they use the positional encoding method. And text, when encoding the text, they use the clip text encoder. And when encoding the mask, they use some CNN layers. And for mask decoder, they use transformer attached with some FC layer for prediction head. Okay, and this architecture, they are saying that very efficient. Okay, and run on a web browser using CPU within this amount of time. Okay, so that's segment anything. So previously, when doing the segmentation, we always train our model using using from some domain and test it on the same domain, right? But in using this segment anything, it can achieve zero-shot segmentation task. Okay, so the main feature of this segment anything is the transformer-based architecture and also the large-scale data set. Okay, if you train that model using large-scale data set, it has generalization ability to generalize in unseen data in the zero-shot manner. Okay. Okay, so given any image, if you input some prompt for point or bounding boxes or some rough masks or some text, then it can generate the corresponding valid masks. Okay, and this rhythm is interactive segmentation method, which was previously the best model. And this paper, this technical report is comparing their performance, their performance with this rhythm, and saying that in multiple data sets, they record better performance even without training on that specific data. Okay, this was trained on that data, but this was not trained. Okay, this is in the zero-shot setting. Okay, for some of the data, it is it performs less than written, but because of the setting, I think SAM is this graph is indicating that SAM is very good. Okay, and this is showing the mask quality by the human annotator, and this is indicating the score for their mask. So ground truth, that's the best. Okay, here. SAM is the next. Okay, SAM, if they are trained to output just one output, I already said SAM is now outputting 3 candidate masks. Okay, but if they are trained to output just one, the performance becomes less robust. Okay, and rhythm is below the SAM. Okay, and also when we give the number, the point as the prompt, their accuracy looks like this. So the SAM is best, but their accuracy becomes better by giving more point. Okay, and this is when giving the center point, and this is when giving the random point. Okay. Anyway, the accuracy becomes better when giving more point as prompt, and also better than others. SAM is better than others. Okay. And actually nowadays, SAM is also extended to language SAM, lang SAM. already Sam could input some text prompt, right? But this was limited to simple word, okay? But this language segmentation, language-based segment anything, they combine the SAM and grounding deno. Okay, grounding deno can receive long text, the long sentence as text prompt, right? So they combine SAM and grounding deno and extend the SAM towards the language-dependent framework. So if you go to this GitHub, then you can test this. Okay. So given this kind of window, you can give some text prompt like person, then the SAM is detecting the person, their segmentation mask. Okay. This is the lang SAM. Okay. So this is very interesting pipelines recently proposed. Okay, they are not published yet. Actually, they are only in the archive and also in the GitHub without any published papers, but they are providing very good performance. Okay. So rather than giving some point to this, just stating the person thing from the image, they can find the corresponding segmentation mask. Okay. And the next thing I want to share with you is the text to image generation method. Okay. So previously, this text to image, it is also done in the domain specific way. Okay. So when you train some generative models like GAN or VAE using some data in some domain and tested them in the data, given the data are in some domain. Okay, so in GAN or VAE, they only operate on some of the domains they are trained on. But here, the researchers want to generalize their approach in some zero-shot setting. Okay, so this is actually the pioneering work in this zero-shot image to text to image generation work. Actually, this is also done by OpenAI. Okay, so given this text, they output the model. Their aim is to make the model to output this type of images. Okay. And even this kind of complex sentence, they want to generate these corresponding images. Okay, this is some ground truth image, and this is the images generated by this DALL-E, and this is the images generated by GAN approaches. Okay, so for example, here, giraffe. This was not properly generated in GAN-based approaches, but this approach the new approach can generate it rather well. Okay, so in new domain, the GAN suffers a lot. Okay, to generate the realistic images, but this DALL-E is able to achieve it. Okay, so they also use the transformer-based architecture, but they make it like the VAE structure, like having the encoder and decoder, right? And they first train using only image data to train this image encoder and decoder. Okay, this is the first step in training DALL-E, and then they align the text features, and they have another text encoder here, and they align these two. Okay, so by doing two steps, this DALL-E achieves this kind of generalized result. Okay. Another stream of work after this, actually, DALL-E was extended to DALL-E 2 and 3, okay? And what they mainly does was using the diffusion models. Rather than GAN or other generative models, they involve these diffusion models, okay? So LDM is maybe some pioneering work for using the diffusion models when achieving the text-to-image generation work. So compared to DALL-E, they are saying that their work is better than DALL-E when generating the in the wild images given the text. Okay, so here this quality is actually better than this is rather blurred in my screen. So compared to this is better. Okay, so using diffusion models, DALL-E it is better than DALL-E. Well, DALL-E is just using transformer architecture. Okay, and stack it like VAE structure, and use some just some VAE like losses to train it without any diffusion things. But this LDM use the diffusion losses and achieve better result than DALL-E. So FID is quite high in DALL-E, but this is far better. PSNR is also like that. Okay, and also it is of course better than the game-based approach. So I briefly want to introduce this diffusion model, but if you want to learn this diffusion model properly, then maybe you have to take the deep generative model class, okay, which is another course will be held in AI.js. Okay, in this class we will tackle some GAN or VAE or diffusion models. Okay, for synthesizing images. Okay, but actually detailing these approaches is actually the beyond of scope of this class. So I will briefly introduce this VAE and diffusion model. Okay, the thing we learned in this class is these networks are differentiable, right? So when given input and output, we can train these networks to input the to output the outputs we aim to obtain. Okay, so in VAE, the input and output is same. So it gives some input X, and this encoder first try to output some feature vector that encodes this input image, and then this decoder is learned to reconstruct the original image. Okay, that's what VAE does. And while doing that, this feature, because we input the training data, right? Training data set X. So this feature is actually trained to, how to say, capture the distribution of this training data. Okay, that's what VAE does. Okay, so while training using only X data as training data for training encoder and decoder, the intermediate features are becoming to capture their distribution. Okay. But in diffusion model, what they does is they first add some noise to the input image. This is the input image, and they actually add some Gaussian noise. So it gradually noised, and eventually will become the some Gaussian noise, some random Gaussian noise, right? And what they do this is actually called the forward pass. This is the forward pass, gradually adding some noise to the original input. then they eventually become some vector which is sampled from the standard Gaussian distribution. And in backward, what they do is they try to recover the original signal using some network. Okay. So using what this network does is, given this noise vector, they try to inverse noising. Okay. So what these networks are learn is the denoising process. Okay. So somehow this structure is similar to what VAE does. It first encoded some feature vector. This feature vector is also following some standard Gaussian distribution, and then they recover it again to the original image signal, right? But here they apply some Gaussian noise and run this backward as the network output. Okay, that's the diffusion model. Okay, they are similar but quite different. Okay, what this LDM does is, in here I explained that we will give noise to signals, right? And we will also do backward to estimate the unnoised signals at each time step. Okay, but we are dealing with the images as input here, right? So if we do this using the images, the time complexity is quite high. So what LDN proposed was, this is latent diffusion, okay? Latent diffusion model, and what they do is, from the input image, this is the encoder and this is the decoder. They first extract some latent vector and apply the forward path of the diffusion model to this latent vector. Okay, so in Z1, they apply Gaussian noise. Z2, they apply another Gaussian noise. Z3, another Gaussian, and iteratively do this to obtain ZT, which is applied T times of the noise process, okay? And then from this noise latent vector, they try to perform the unnoise using this UNet structure, okay? And using this UNet is trained to recover the original signal. For example, T-1 is output, GT-1 is outputted from this UNet architecture, inputting this G of T, okay? These reverse approaches are done by this UNet structure. Anyway, so it recovers the original signal using this UNet structure, okay? That was actually the process happening this. And then you have to make it to apply this until you get Z1, okay? And at the last step, you also combine some of the additional prompt, like the semantic map text, and some other representation could be the prompt, and you also combine them to the inverse process, okay? And recover anyway the Z vector, latent vector. And using that latent vector, using the decoder, you reconstruct the original image, okay? So the difference to original diffusion model is this latent diffusion model, they apply diffusion stage, the backward and forward steps, they apply that in the feature space, okay, rather than in the image space, okay. So by doing that, you can accelerate the computation, okay. So LDM is also can generate high resolution images because you can reduce the complexity of the model, okay, by applying diffusion process on the feature space rather than the image space. Okay, and this is the loss function for LDM. So basically, in each time step, this is the diffusion time step. So T means you are inverting T to TZ minus 1, okay? This T is for that, and this is some prompt, and this is the latent vector in G step. And you want to inverse it towards some noise, which is the Z actually, okay? So each UNet is trying to inverse the noise signals to a noise signal, okay? That's the happening in LDM. So this is the diffusion process, and via this diffusion process, the image generation quality, this is becoming better than DALL-E, which is not using the diffusion model, right? And DALL-E 2 is also involving DALL-E, involving diffusion model to original DALL-E. Okay, they are actually trained with the same data, but involving some diffusion model inside the model. Okay, so what they does is their pipeline is slightly different from previous DALL-E. So here is the text prompt. Okay, and this text encoder is the actually same as the clip text encoder. And this is the image encoder. And this is the image input. And so first step is same as the clip things. They first involve the data, image and text pairs to align the text feature and image feature and train this text encoder and image encoder. That's happening in the first step training in the DALL-E 2. And then the next thing is you using this text feature, you actually learn this decoder part. So this is the name of DALL-E. Another name of DALL-E 2 is on-clip. Okay. So using the encoder image features or the text encoder, you first input this text embedding feature, right? And via this decoder, you unclip to generate the images that fit to this text encoder, this text feature, okay? And this decoder is also involved with diffusion process. And also these things, improving the features inside this step, the diffusion is also used, okay? And actually in this paper, they involved just transformer-based approach and compare this baseline with the diffusion baseline and saying that diffusion by involving diffusion in this process, the performance getting better, okay? They are insisting that. So this is the comparison. This prior thing is here, right? So AR is auto-regressive. This is indicating the transformer architecture. And this is the diffusion process. And they are getting better photorealism and the caption similarity and diversity compared to the transformer-based one, okay? So they are insisting that we have to involve diffusion process. And also they record better performance than other text to image generation type frameworks, okay? So this is the zero-shot testing result and getting better performance. And compared to diffusion and non-diffusion model, diffusion-based one is better, okay? This is some result, okay? But one thing that faces this DALL-E 2 is currently having many weaknesses, but one of the most important thing is this problem, prompt following issue. Okay. What they mean is they sometimes just ignore some of the word in the text prompt. Okay. So when you try DALL-E 2 or other diffusion-based text-to-image generation framework, then you can frequently feeling that these approaches, this method are generating something related to the text prompt, but that's exactly, sometimes it is ignoring some of the words in the prompt, okay? That's actually called as prompt following issue, okay? And two paper published in NIPS 2022 was using the large language models as the prompt encoder, okay? So they actually just involved this by fixing them and train another inverse network for generating the images from this encoded text feature. And they are reporting that surprisingly, this kind of method is working very well. Okay, that's actually Imagen. Okay, and this is done by Google Brain. Okay, so that paper is actually trying to solve this prompt following issue by involving some large language models that can understand very well on the text prompt. Okay, and they can solve that kind of problem. Okay, and also they propose new benchmark that have relatively complex prompts and including long, intricate textual descriptions and rare words and misspelled prompt. Okay, so previous image text pairs, they are insisting that they are not very good for evaluating this prompt following issue. So they propose new benchmark having this kind of challenges in their text prompt. Okay. This is another contribution of theirs. Okay. And DALL-E 3 was newly introduced in this year. And this is also maintained by OpenAI. And they are also tackling the prompt following issue, okay? But their contribution is improving the image text pair data quality, okay, rather than proposing new algorithm by involving some image captioner, okay? So this is DALL-E 3, and you can see their text prompts are rather low, very low compared to the previous approach. Even from this long sentence, you can generate proper images, okay, that fits to the text prompt. Okay. So this is actually the state of the art for this zero-shot text-to-image method. Okay, so far we saw a lot of foundation models. Okay, and their lessons are like this. So involving large-scale learning, large-scale data on transformer models, it makes the model to generalize to new unseen data. Okay, we can even test on the unseen data in the zero-shot manner, and it can outperform the models which was trained in the supervised way. Okay, so good task agnostic. This is zero-shot and few-shot performance. Okay, so even in vision research, combining the language to some of the features inside the vision models that can provide promising way to achieve the zero-shot learning. Okay, so this is some lessons we can take. Okay. Okay. So and this is the notice again. We will have the quiz next Wednesday. Okay, and this is open book. All course materials are ranges. We will have only 10 questions, and which is the multiple choice questions. Okay, 객관식입니다. 객관식. So let's finish here. Okay, see you next Monday.